Okay, this video is going to show you how to figure out the hybridization around a central atom in a molecule. At first, I'm going to go through a little bit about hybridization, but the main thing that you need to be able to do for this course is just to be able to determine what the hybridization is on a central atom. So here we go with this. So here's kind of how the theory goes with hybridization. And so let's say that we had CH4, and you could draw the Lewis structure, and you would say C, and it's going to single bond with 4 hydrogens, carbon with 4. So there's the Lewis structure. Now, if we look at hydrogen, its electron configuration is 1s1. And so if you remember orbital notation, it has 1 electron in an s orbital. And then carbon is 1s2, 2s2, 2p2. So its orbital notation has 2 in the s, the 1s, but those electrons aren't involved in the bonding. It's the 2s and the 2p. Those are the electrons that are the valence electrons that are in bonding. So it has in the 2s it has 2, in the 2p it has 2. Now, here's kind of how this would look then if we took a look at this Lewis structure. If I start over with it, instead of drawing it the way I did, we have carbon. It has 4 valence electrons. 1, 2, 3, 4. And 2 of those electrons are from S, the 2s right here, and 2 are from the p's. All right? Now hydrogen, all of its electrons are just from the 1s, so they're all s electrons. So hydrogen would be over here. So they're all the same. Well, when people look at the bonds in this methane, CH4, what they find is that these 4 bonds are identical, even though 2 electrons from carbon are from p orbitals and 2 are from s orbitals. Now, if that was really the case, that they were different in energy, then these bonds wouldn't be the same. So what people theorize is this is what happens. And so carbon has this 1s2, 2s2, 2p3. All right, so it has 1s2, 2s2, 2p2, I said 2p3. So here's the 2p, here's the 2s. Those are the valence electrons. Well, here's what they think that happens. All right, so what they think is that what carbon does is it takes this s, one of these s electrons, and it promotes that electron to the a p orbital. And then what happens is here we have the 1s. These electrons, because of the one that was promoted, it makes 4 orbitals of equal energy with 1 electron in each. Now, to name them, you really can't call these s orbitals because one of the orbitals was from a p, or from one of the orbitals was from an, or one of the electrons in there was from the s, and you really can't call these p orbitals because 1 electron from the s, the 1s, was promoted there. So we have 4 orbitals of equal energy. So what they name them is they call them hybrid orbitals, kind of a blend of the two. And instead of calling them s orbitals or p orbitals, they call them sp orbitals. Now, what you're going to have to be able to do is, given a molecule, you would draw the Lewis structure, and then the question that you would have to answer is, what's the hybridization around the carbon atom? Well, it's really easy to figure out. Now, this is the easy part, is figuring it out. The hard part is kind of explaining what I just did there, which you don't really have to worry about for our class. But what you do have to worry about is being able to figure out the hybridization. So let's look at this carbon, and the question would be, what's the hybridization of the carbon? Well, you just count the domains around the carbon atom, and the number of domains will tell you how many of these hybrid orbitals there are. Now, the answers for hybridization, there's 3 types that you got to know. There's sp, that means you're using one s orbital and one p orbital to make two hybrid orbitals. There's sp2, which means you would be using one s and two p's for three hybrid orbitals. And there's sp3, which means you would need four orbitals. Well, if you count the domains, that will tell you what the hybridization is. So if you look here, we have 1, 2, 3, 4 domains. So which combination of S and P adds up to 4? Well, it's sp3. So if somebody asked you, hey, what's the hybridization of this carbon? You would just say 4 domains, so it must be sp3, because 1 plus 3 equals 4, which equals the domains. All right, let's look at another example. So let's say somebody said, okay, what's the hybridization of the nitrogen in NH3? Well, what you would have to do is you would draw the Lewis structure, and you would end up getting this right here. And somebody said, okay, what's the hybridization of the nitrogen in sp3? Well, you just count the domains of electrons around the central atom. So there's 1, 2, 3, 4 domains. So you need a combination of S, which is always 1, and P, that adds up to 4. So it's going to be sp3, because 3 plus 1 is 4. There's 4 domains. Okay, let's look at another example. Okay, CO2. Well, step 1 is you draw the Lewis structure. Carbon bonds to oxygen. I'm going to kind of speed this up. You should know that it will double bond, and you will get this Lewis structure. So somebody might ask, what's the hybridization of this carbon in CO2? Well, you just count the domains. And so the domains, remember there's 4 possible domains, but in this example, we're only using 2 of them. We're not using the one here or here. So this only has 2 domains. And so it's going to be what combination of S and P adds up to 2? 1, it's just going to be sp. So this carbon is sp hybridized. Okay, a double bond you don't count as more than 1 domain, if you remember that. Okay? Okay, the last one would be CH2O. So you have a carbon, it double bonds to the oxygen, and then you have a hydrogen here and a hydrogen here. This oxygen would have a couple lone pairs. Okay, that's the correct Lewis structure. You can draw it if you want to make sure, but it's correct. Anyway, so you count how many domains are around the carbon atom. Okay, so there's 1, 2, 3 domains. That means you need 3 hybrid orbitals. So what combination of S and P add up to 3? 1 plus 1 S and 2 P's. So this would be sp2 hybridized would be the right answer for formaldehyde. Okay, that's it. All right.
Good.
Are you going to go into an example with the double bond, like you did with the CH4? Or are you just going to say that you, at this point, all you have to do is count the domains?
Just counting the domains. Because a double bond is 1 domain.
Yeah.
I think that's all I'm going to do. There is something, that animation, it shows how the hybridization, it shows like how one of the bonds is a sigma bond, and that would be the hybridized orbital, and the other one is a pi, which isn't the hybridized. But I don't think we need to go into that too much.
So what are we saying